So here the energy balance models. This is mainly based on the influence of surface albedo and the snow ice line on polar temperature sensitivity. This was the very earlier model that was developed. Then early climate models, Manabe and Sellers. Manabe received the Nobel Prize for many of his studies related to the atmospheric science. He talked about vertical and horizontal heat transport, the impact of surface albedo change on near surface temperatures, and use of horizontal heat transport as a critical factor influencing polar amplification. So these are all the stepwise approach people had included in understanding how the Arctic amplification actually takes place. So then came the general circulation model. So here the simulation of atmospheric dynamics and confirmed polar amplification structures and mechanisms were developed. And here we integrated ocean dynamics, revealing that seasonal variation in polar warming and the role of ocean heat transport is included in the Arctic amplification models. And then we have the climate model, where people included the ocean heat transport and its influence on Arctic climate sensitivity. Then there are other models which are based on statistical dynamics model. So here radiative convective model, here only the vertical dimension is used, that is vertically how much is the difference that we have seen. And the next one is the sea level temperature, here only the horizontal dimensions are used. So these are all the statistical dynamic models. And then Arctic regional climate model is mainly for the regional atmospheric climate model. The first one is the ICON, that is icosahedral non-hydrostatic large eddy simulation model. So this is to evaluate the boundary layer and surface process in the sea ice covered central Arctic. And Hirham model, this is to evaluate the precipitation and snowfall simulation. Then community land model, this reduces the active layer thickness and winter soil temperatures. Then Hiram Nausim atmosphere ice ocean model. So here it is improved parameterization of processes related to the snow on the ice, open water leads, and the heat and momentum exchange at the air, ice and the ice oceans interfaces are included. Then we have the CMIP model, that is the coupled model intercomparison model. We have come up to CMIP 6 type. So these models simulate the physics, chemistry and biology of the atmosphere, land and the ocean in great detail to generate current and future climate projections. The number of future scenarios examined and the number of different experiments conducted are based on this particular model. Now let us look at the challenges faced by the earlier global models. So there were inadequate topographical information. So this is the major problem in the Arctic region, because there are plenty of fjords, mountains, valleys and other things. So we only had the low resolution images earlier, and also incomplete data on the cloud and sea ice distribution. So this was one of the limitations. Then advection and moisture are not properly accounted for. So that means precipitation cannot be measured very effectively. Intra and interannual difference in Arctic circulation was not included, and measuring and incorporating tropospheric temperature was not done. So these are all the limitations in the earlier models. And of course, missing information on cloud radiative process, ice crystal formation, permafrost, surface hydrological process, terrestrial marine source and sinks of trace gases. So all these things were not included. And also release of heat from sea ice leads air temperature fluctuations. And finally, the relationship observed between the precipitation accumulation and atmospheric circulation. So these were not included in the earlier model. So that's the reason those models could not predict the Arctic amplification very effectively. Now let us look at how these models are generally built. The first stage is the analysis of the feedback is a powerful tool to study dynamic systems. So that means if we know the feedback, then we can actually understand what is the cause and effect. So that is the very basic fundamental thing we need to know, and that is how the dynamic systems can be modeled. So if we can identify the pattern or cause and effect, this allows us to create or study a dynamic system using mathematical descriptors. So one of the major issues in defining the boundaries, because Arctic is a vast region and sea ice we cannot even know, where the ice is present, where the ice is not present. So the defining the boundaries are the biggest problem. And also Earth or global climate system is an open system, so the description of the system is even more complicated. Some changes of parameters may be relevant in the future or maybe no longer be relevant, nonlinear, abrupt or irreversible. So this is another big problem, because we may be using a parameter which is existing only for few years. Previously it may not be existing, maybe in the future it may not even exist. So that means these are all the limitations of developing the model. Some parameters are transient. As we can say, cloud is extremely transient, so we cannot exactly say or use how much cloud was present when and how, all these things. So this is another issue, and some of the things slowly change, so that is also very difficult to model. And there are top-down methods in which the global feedback is inferred from a global energy balance equation. There is also bottom-up method where the total feedback is an emerging property of the different process that we try to model quantitatively based on the insight into each process and data obtained to constraint or parameterize it. So these are all some of the assumptions people make while building the model. So what is the real crux of this thing? We actually want to know how the Arctic amplification is happening and can we predict what is going to happen tomorrow. So that is the very objective of this one. We carry out or create models to understand and study is simply to see in future what is going to happen. So is it very easy or difficult to predict the future? We cannot predict the scale, that is the magnitude or occurrence, that is when, which day, what event will occur, especially with related to climate change. This is not possible. But human choices like anthropogenic activities, natural variability and scientific uncertainty can be understood. And human choice means change in population, energy requirement, use of technology, emissions. So these can be controlled, and once we can actually have some rough idea whether it is the right choice we are making or not, that we can actually understand if we know the model. Because what is going to happen tomorrow, if we know, if we can reduce some of the emissions, if it is going to reduce the global warming, then we can actually make some attempt to achieve this. So that is the reason we do need to understand that. And there are natural variabilities which we cannot even predict. For example, climate sensitivity to constituents. Similarly, change in precipitation, that means atmospheric circulation, storm tracks and moisture convergence. Many of these natural changes or even forest fires, extreme weather events, it's very difficult to predict. Similarly, there is scientific uncertainty, that means parametric uncertainty. We are unable to create spatial or temporal scales smaller than they can resolve. So if you are talking about a satellite image, it is running in kilometers. So if you want to go in millimeters level or centimeters levels or at meters level resolutions are possible, but not at the centimeters level or so. So that means going deep into that is also a big problem. And the structural uncertainty is another big problem we face. So this is quite difficult because of all these limitations. It's very difficult to develop a model where we can have a better understanding of what is going to happen in the future. So here is a simplified conceptual framework for the climate system. So we have plenty of feedback process, and this feedback process plays a vital role in the Arctic amplification. So all these things leads to the climate impact, and more about this chart will be given in the textual content. So here when we talk about this framework, we are including the radiative balance, temperature changes in other climate variables, effective radiative forcing and instantaneous radiative forcing. These radiative forcings are based on various chemical reactions that are occurring, and also the release of carbon dioxide, non-carbon dioxide, greenhouse gases, aerosols, land use, volcanic eruption, solar irradiation. All these things are called climate forcing agents. And we will be looking at many of the climate forcing agents in the later part of this course. And there is also ocean acidification, and ocean acidification also affects the climate.